review, make sure that we know the topics to be expecting. So I do want to spend the first 5 to 10 minutes just kind of going over the trig derivative rules. Okay, so we'll do a practice problem with that. Implicit differentiation, we've seen that yesterday, day before. Particle motion, I'll probably do one of those problems tomorrow. Related rates, we'll do one today. Mean value theorem, trig, derivatives, average rate of change. We did that on the first day. I'll go back and I'll redo that problem again with you. We'll do a curve sketching today, and we'll do a curve sketching tomorrow. So each day I want us to just have just get that practice in with curve sketching. Make sure you know your unit circle values. Okay, if you like, I can give you a blank unit circle sheet when I pass out the test, so that you can use that to fill out and use those values to help you with your curve sketching. Okay, no calculators. Okay. So let's spend some time reviewing through our derivative rules. Now, as far as derivatives go, the big three are these three here. So power rule. We've been using power rule ever since August. E to the U.
This is an emergency.
What?
That sounded like code, yeah.
Oh, yes, yeah, over there.
Just like you saying it helps.
You said that so.
Are we hiding? Someone.
No, sorry,
said,
guys.
like, I'm like, don't use the mic.
Yeah.
Okay, so the derivative rules, power rule, e to the u times u prime, or e to the u, and natural log is e prime over u. So these are the ones that guarantee to show up on the AP exam. We need to just always commit these to memory. Okay. Now, let's review through the 6 trig derivative rules that you guys were responsible for on the quiz, which will also show up on the test. So, yeah, can get on a sheet of paper. Go ahead and write these rules down and see if we can practice recalling these rules, and then we'll shift over to our trig. Okay. So either on a separate sheet, or if you can find any space on. So I like to have these trig functions ordered in this way. It helps me remember and see nice patterns that help us with memorizing these rules. So 2 columns, lining up all the C functions in alphabetical order. Sine and cosine are next to each other. They have similar patterns. Tangent and cotangent have similar patterns. Secant and cosecant have similar patterns. All the C functions produces negative derivatives. Okay. And the similarities is this: sine and cosine, they only involve each other for their derivatives. Tangent and secant, they only involve each other for their derivatives.
Sorry for the interruption. Please disregard the alarm.
And then cotangent and cosecant, these involve each other. All right, so see if you guys can recall those rules, and I'll go over them. I'll show them in a second. Okay, let's check our rules here. Okay, sines, derivative is cosine. Cosine is negative sine. Tangent just involves the one right below it. Tangent is secant squared. Secant is secant tangent. All right, if you can put this down, then this follows very similar pattern, right? Cotangent is just the one below it, negative cosecant squared. Cosecant is cotangent, negative cosecant cotangent. Yes.
If we switch, like tan and secant.
Yeah, that doesn't matter. That's fine. Okay, so we'll review these rules again tomorrow, but hopefully we're able to commit this to memory, just reviewing them from what you guys were able to do on the quiz. Okay, let's go over our trig rules. So in a sense, this is easier and harder at the same time. So first off, you're going to kind of order them the same way. So basically, just copy everything down from your original 6 trig rules, but just put arc in front of each of them. Okay? But the order is going to stay the same, or the pattern is going to stay the same. 2 columns, okay, 3 rows. The easy thing is that there's really only 3 rules you have to worry about, because these 3 are really just the negative versions of the ones next to them. Okay? So, but the reason why these look so complicated is because there's a lot of things going on, right? You got the absolute value, you got the square roots. Okay, there's a lot of parts that make things look complicated. But I want to build them from similarities, right? If I can identify all the similarities, then it just feels like I'm just do a little bit more to adjust for each derivative rule. So arc sine, well, first off, they all involve fractions. Okay, so that's something that is nice similarity between each of them. Okay, so they all involve fractions. And then, what do you know about all the numerators?
They're all U prime.
They're all U prime, so that's nice. That just makes it easier to deal with. And then the denominators, they look different, but they all have what?
We have U.
Yeah, they have U squared, and they all have 1. Okay, they all have 1, and they all have U squared. So I like to start with arctangent. Arctangent is the simplest looking one. There's no square root, there's no absolute value, there's no minus sign. It's just 1 plus U squared. You can change the order if you like, but just 1 plus U squared. So if I can commit that to memory, I feel like I can build the other ones just from that information. Okay, arcsecant. Next up, I like to go to arcsecant. Arcsecant is the most complicated looking one. It's got the absolute value, it's got the square root, it's got the minus sign. So I like to do this. Just start with what I know. I know that there's a 1 in U squared that's going to be inside the square roots, but the order, that's something we have to kind of talk about, right? What order is it? So what helps me remember is the fact that I know the U's are going to sit next to each other. So it's going to be U squared minus 1, and not 1 minus U squared. Having that in front of me makes it easier for me to decide what happens with arcsine. Because arcsine looks a lot like arcsecant. I think what makes things complicated, or what confuses students, is they forget, right? Which order is it? We know that the order is different, but we forget which one it is. But if you can see U squared minus 1 here, then that kind of informs me that, okay, there must be a different order for my arcsine. So that helps me remember I have 1 minus U squared there. And if I can fill these 3 out, then the ones next to them are just negative versions of them. All right, so take a minute to look at these rules. And then in a minute, I'm going to erase them and have you guys try and see if you can recall these rules from memory. Okay, ready to try these? Okay, so find a fresh sheet so that you're not able to see the rules on your page and see if you can recall these from memory. Okay, all right, let's check our rules here, see how we did. Okay, so we have another day to practice these rules tomorrow. Why don't we try this problem here? So let's do a problem where we can practice applying our trig derivative rules. So if you can copy this down. Okay, so we know we definitely have to involve the rule for arc secant. U prime over absolute value of u times square root of u squared minus 1. What else do you see? What else do we have to make sure that we apply? Okay, good. Power rule. Good. So we have to make sure we don't overlook the need for product rule, right? F prime g plus f g prime. So all right, try that. See if we can step through the derivative for this function. Okay, f prime g, so f prime x becomes 1. Keep the original g function. Back to f g prime. So when we get a g prime, we have to involve our sequence rule. What's u prime going to be? Just 4, okay. Absolute value of u. Square root of u squared minus 1. This whole expression gets squared. Okay, and don't forget the last term, minus 20x cubed. Okay, you'll need to find common denominators. We're just going to do a little bit of cleanup within each term. Okay, questions there? Mm-hmm.
X on top and X before. Is that not able to-
It can't. Yeah, why is that?
Is the absolute value
Not because of that.
being multiplied? Oh, it's being subtracted.
Yeah, that minus 1 causes all sorts of trouble. Now, if it was just necessarily 4x, then yeah, we can take this out. Anytime there's an addition, subtraction involved, you got to be extra careful. We can't cancel it out unless it's an exact perfect match above and below. Okay, so expect to see something like this on the test where you have to involve derivative of arc trig. Okay, let's go to worksheet 3. And let's do a curve sketching problem. So we can go to the back of worksheet 3. Let's do a full curve sketch problem. So number 5. I'm going to put this on a separate sheet just so that I have enough room. So feel free to do that if you'd like to do that as well. Half a page may not be enough, so just to let you know. Okay, so sketch the function, sketch the graph of sine of 2x. Let's just start off by gathering some information. We're going to find, from f, we'll find f prime. From f prime, we'll find critical points. From critical points, we'll populate the sine line. Test each subinterval. Determine relative max, relative min, increase, decrease, and then we'll do the same thing for the second derivative process, critical points, sine line, points of inflection. Okay, so here's our function. Okay, so let's start off with finding f prime. Sine of u becomes cosine of u times u prime, right? So cosine 2x times 2. We'll set our derivative equal to 0 to find our critical points. Okay, I can divide by 2. Two goes away, I'm just left with cosine 2x. Now, we're not going to rely on double angle identities. We're just going to rely on inverse trig and division. So I'm just going to isolate that 2x, that parentheses by itself. I'm going to move that cosine over as inverse cosine. Okay, so 2x equals inverse cosine of 0. And we have to ask ourselves, when is cosine of theta equal to 0? Because that's what this notation means. Another way of saying this is, figure, tell me cosine of theta, tell me theta that causes cosine of theta to be 0. And, okay, so if you that's why it's important that we know our unit circle values, right? Cosine of theta is equal to 0, x value, so cosine of theta is equal to 0 at pi over 2, and also at 3 pi over 2. Right, x value is the cosine. So pi over 2 and 3 pi over 2. Now, we are anticipating that we're going to be dividing by 2, which means that our angles are going to shrink. So we're going to find some additional potential solutions that extend past our normal interval from 0 to 2 pi, because of the fact that if we shrink all these values, we may be potentially missing out on some larger measures that end up shrinking into the interval from that we're looking for. So it's always a good idea if you're anticipating shrinking your angle measures, that we're adding 2 pi so that we can ensure that we have all the solutions that we need. So if we add 2 pi, that's another way of saying plus 4 pi over 2, just so that we can match common denominators. So if I take my additional values, my initial values, and add 2 pi, what's pi over 2 plus 4 pi over 2? Okay, let's keep going. What's 3 pi over 2 plus 4 pi over 2? 7 pi over 2. So we're going a little further out because we know our angles are going to shrink. Okay, let's divide by 2, which is the same thing as, okay. 1/2 and 2 cancels out. Multiply this through. Pi over 4. 3 pi over 4. Okay, everybody okay with this process? Inverse trig to pull angle measures, adding additional potential solutions, because we know these values that are outside the interval may shrink into our interval all of a sudden. Okay, so now that we have our solution set, let's check against our interval here. We only want from 0 to pi. So are any of these values greater than pi? Yeah, 5 over 4 is greater than 1, and so is 7 over 4. So I always like to eliminate values outside the interval, so that gives me reassurance that I didn't accidentally not go far enough, right? So I have two critical points, pi over 4 and 3 pi over 4. Now I'm going to place them onto the slope sine line, derivative sine line, so I can gather information about slope and subintervals and intervals of increase, decrease, as well as relative max, relative min. So we start off at 0, we end at pi. Critical point, pi over 4, and 3 pi over 4. Okay, we're going to test values against the first derivative function. Let's choose some convenient values that land inside the interval. So between 0 and pi over 4, I can choose pi over 6. Between pi over 4 and 3 pi over 4, I can choose pi over 2. And between 3 pi over 4 and pi, I can choose 5 pi over 6. Okay, I'm going to insert these test values in for x of the derivative and see if I get positive or negative values. Okay, so first up, I'll test pi over 6 in for x. So 2 times pi over 6, I can reduce the 2 and 6 to be 1/3, or pi over 3. What's cosine of pi over 3? First quadrant, right? So cosine will be what? Positive, right? So that's all we need to know. Okay, next up, let's test pi over 2. Figure out whether the slope is positive or negative. Insert pi over 2 in for the x of my derivative. Two's canceled out. I'm just left with cosine of pi. What do you know about cosine of pi? Negative. Okay, so 2 times -1 is negative. My graph is going to be falling in that interval. Next up, we'll test 5 pi over 6. This becomes pi over 6 over 3. 2 and 6 reduces. And cosine of 5 pi over 3, that's in the fourth quadrant. So what? Positive. Okay. Okay, so we know where the graph is increasing and decreasing. What do you expect at pi over 4? A relative what? Max, okay. And at 3 pi over 4, a relative min, right? Falling, followed by increasing. Okay, so we're going to eventually find all those order pairs and plot those points and sketch our graph. But let's move to the second derivative and gather information for f double prime. Okay, so we start off with f prime. We go through our derivative process. 2 is going to stay. What's cosine of u going to turn into? Negative sine of u times u prime. So 2 stays. Cosine becomes negative sine. We keep the parentheses. but then we multiply it by the inner function's derivative. The u prime is going to be 2 times 2. Okay, let's do some cleanup. Let's collect all the coefficients. 2, negative, and 2 becomes -4. Yes. That's fine. Yeah. So that's what I was about to do. I'm gonna pull all the coefficients out in front to make it a little cleaner. Good. So yeah, it just makes it easier if all the coefficients are together. Okay. Any questions so far? Are we good with second derivative? Okay. So just like before, now that we have our second derivative function, we're going to find critical points set equal to 0. Divide both sides by -4. It'll just go away because of the 0 on the other side. So we have an easier thing to test now, or sorry, to gather our critical points. We're just going to look to see where sine of 2x is equal to 0. Okay, again, let's not deal with double angle identity. We're just going to rely on inverse trig. So we're going to force that sine over to the other side. So we're going to ask ourselves, when is sine equal to 0? When is sine equal to 0? Unit circle values. Yeah. So if we look at unit circle values, sine is the y value, right? So sine of 0 is going to be at 0, pi, 2 pi. So I'm going to go a little further than what we have initially. We know that we can always add 2 pi to our original values to get coterminal values that are the same. 0 plus 2 pi is 2 pi. Pi plus 2 pi is 3 pi. Okay. I'm going out a little further out because I'm expecting these values to shrink and potentially shrink into our interval. So divided by 2, same thing as multiplying by 1/2. One half and 2 cancels out. Okay. 0 over 2 is just 0. Pi over 2. 2 pi over 2 is just pi. And 3 pi over 2. Okay, f prime, f double prime. Well, first off, our subinterval is only from 0 to pi, so I can eliminate 3 pi over 2, right? But these are duplicates. These are endpoints, so we're going to put this onto our sine line. Okay, let's choose values in each subinterval to test against the second derivative function. So convenient value between 0 and pi over 2, I'll choose pi over 4. Between pi over 2 and pi, I'll choose 3 pi over 4. Okay, so pi over 4 in for x. So this just becomes sine of pi over 2. Sine of pi over 2 is just equal to 1, right? 1 times -4, that's negative. So I know that my first subinterval is going to be negative. Second derivative, that's going to be concave down. Okay, let's test 3 pi over 4. This will reduce down to sine of 3 pi over 2. Sine of 3 pi over 2 is negative. Negative times negative is positive. So I know that this subinterval is going to show concave up. Okay, so everything that we need is here. Now we're just going to have to start transitioning over to plotting our points. So I'm going to go back to my original function, and I'm just going to find order pairs at the endpoints, order pairs at the critical points, relative max, relative min, as well as order pair of the point of inflection. So I'm going to go back to the original function here, and then start to gather information about my locations. Okay, so I'll start with the endpoints. Sine of 0, sine of 2 times 0. Which is 0. F of pi. Okay, moving on to some critical points here. Let's test pi over 4 and 3 pi over 4. Find those order pairs. This is sine of pi over 2. Sine of pi over 2 is 1. Sine of 3 pi over 2 is going to be negative 1. And then one more, we also want to test our find location of our point of inflection. This is sine of pi, which is 0. So we have all these order pairs. Let's go ahead and plot them onto our graph. And then we can connect those dots. So 0 is 0. At pi over 4, my order pair is y value is 1. At pi over 2, back to 0. At 3 pi over 4, down to negative 1. And then at pi, back to 0. Okay, based off our slope sine line, I know I'm expecting a relative max at pi over 4, so my graph is going to rise to that point. It's going to fall to 3 pi over 4. And it's going to rise to pi. Okay, between 0 and pi over 2, I know I'm going to go over my graph again, give it the curvature that it needs from 0 to pi over 2, concave down. From pi over 2 to pi, concave up. Okay, there's our graph. Yeah, so absolute max, absolute min. We just have to look at the graph and identify the highest and lowest y values. Yeah, so if you have the graph in front of you, you just identify those y values. So see if you can spend a minute to fill out the A through D, or the information that they're gathering. You can just pull all that from your sine lines. but let's practice writing out our because statements, right? Make sure that when you write your because statements that you don't just say because it is increasing or because it is changing signs. You want to make sure you specify what it is, right? Name that function. Is it f prime? Is it f of x? Is it f double prime? Okay, try that. And then absolute extrema, absolute max is the highest y value that you see. Absolute min is the lowest y value that you see. You should be able to just pull that from the looking at the graph. All right, let's do one more problem. Let's turn to the front of worksheet 3 and work through a related race problem. Yes. Let's see, where did I get that points? Here we go. F of 0 is 0, f of pi is 0. Okay, so let's look at number 1. Related race problem here. Okay, so the diagram is going to be drawn for you, but let's see if we can practice just reading the problem and putting it down on the graph. Put it on a triangle. Okay, suppose a bird is flying horizontally 40 feet above your head. Okay, so the bird is flying horizontally here. Observer down here. So that bird is going to hold that altitude of 40 feet. So we know that that vertical height is not going to change, so we can put a constant there. But the bird is flying horizontally away from you, so you know that this horizontal distance is changing. So we'll put an X there. How fast is the angle of elevation changing? So theta is going to be here when your horizontal distance from the bird is 30 feet. All right, let's just go ahead and start with our trig function. We know we're going to have to involve a trig function that's going to hit the values that we see in front of us. Now, you could end up using any of the trig functions if enough information is provided about all three sides, but here, no information is provided about the hypotenuse. We're kind of forced to rely on just the x and the 40. So which trig function is going to hit theta, x, and 40 for us? Tangent, right? Tangent is opposite over adjacent. Okay, so we want to find the derivative, but before we find the derivative, what should we do to make this a little bit easier to work with? Rather than going through quotient rule, we can, yeah, to -1, right? So that we can just rely on power rule and not quotient. Okay, let's go ahead and find the derivative. Remember, time is involved because of related rates. So tangent theta becomes what? Good. So the variable is theta, so we're going to attach a time component for that variable. Right, the right side. What does power rule give us? Times. Good. Every variable has a time component. Okay, so we can definitely clean this up a little bit, but let's just go ahead and go back to the problem, see if we can gather some information here. Bird and assign values to variables. 40 feet above our head, we know that is a constant. The bird is flying horizontally 20 feet per second away from you. So what can we assign 20 to? Good. We know it's movement. We know it's going to be horizontal. This is going to be related to x. So imagine there's another x up here, right? It's going to be the same thing, horizontal distance away from the observer. So dx dt, positive or negative 20? Positive, because x is increasing, right? The distance between you and the bird is increasing. So positive 20. How fast is the angle of elevation changing? What are we looking for? When your horizontal distance from the bird is 30 feet. That's just x. Okay, so if we look, we have a suitable substitution for x. We have a substitution for dx dt. We're looking for d theta dt, so that's showing up. So then the one thing that's new about this process is dealing with the trig ratio. Okay, so make sure that you're not stuck trying to figure out what theta is. We don't need theta. Okay, all we need to figure out is the ratio for secant of theta. So use another space to draw a separate triangle, and here we're going to use this to help us figure out the ratio that we need, so that we can replace this entire secant of theta. Okay, so let's fill out all the sides. We know the height is 40. What is the x value at this moment in time? 30. So you're always going to be given enough information to find that third side. Okay, and Pythagorean theorem is how you're going to get to that third side. A squared plus b squared equals c squared. You can recognize this as a 3, 4, 5 variation of the 3, 4, 5 triangle. Okay, we need to find a substitution for secant of theta. What's secant of theta going to be? Good. We know secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse, which means that secant is hypotenuse over adjacent. So secant is just 50 over 30, which can reduce to be 5 over 3. All right, so we have everything that we need now. Okay. We're going to square our ratio. D theta dt is going to stay negative 40 over x squared. And I'm going to replace x squared and dx dt with what we've gathered from the problem. Okay, clean up along the way here, 25 over 9. Okay, how do I bring the 25 over 9 over? Reciprocal, so the right side will show up as (9 over 25). Okay, this looks difficult to clean up without a calculator, but if I just break everything down, in terms of easier numbers, right, I can think of negative 40 as negative 4 times 10, 20 as 2 times 10, 30 squared, that's 30 times 30. I can break 30 down into 3 times 10, 3 times 10. Just makes it easier. If I have a bunch of small numbers, it's easier to cancel out. Right, this is 30, that's another 30, 25. And if I can match numerator and denominator, I can cancel out a whole bunch of stuff. The 10s cancel out. 3 times 3 is 9. So what's left over is 4 and 2, or negative 4 and 2, which is negative 8. Denominator is 25. Okay. And what's our unit of measure? Good. Theta is always radians, never degrees. And then time component is seconds. All right, we'll pick up tomorrow. Help session this afternoon.